Hello, this is Melaku Lemma, a PhD student at the University of Coimbra, working under the supervision of Professor Carlos Rebelo and Professor Simoes da Silva. Today I'll be presenting a part of the work we did on the seismic design and performance assessment of steel frames considering the joints behavior. My presentation today is organized as follows. First, I'll be presenting a brief introduction into the topic, and then the seismic analysis and design of three frames disregarding the joint behavior will be presented. This will be followed by the global performance assessment of these frames through the nonlinear analysis performed. The results will be presented, and this will be followed by the redesign of the same frames, this time considering the joint behavior. Finally, some conclusions will be drawn. The Equal Joints project studied 4 joint topologies, 3 of which are bolted joints, while the last one is a welded joint. Our focus in this presentation will be laid on the bolted joint type 2, which is an extended stiffened end plate joint. The Equal Joints project considers the use of semi-rigid connections in seismic conditions and also proposed an additional classification of a joint which is termed equal joint, which ranges between partial and full strength joints. The Eurocode allows for 3 simplified joint models, which are simple, continuous, and semi-continuous models, and the behavior of joints could be predicted using either of these 6 methods listed here: analytical, empirical, experimental, mechanical, numerical, and informational models. Once these models have been identified, it will be fed into the structural analysis program. And in doing so, there are different methods of modeling, mathematical models with different degrees of accuracy. There are linear models, nonlinear models, and bilinear and multilinear models in between. In terms of modeling the joint in structural analysis programs, the most common and mostly known models are the centerline models. These disregard completely the dimension of the joint node. The scissors model is an improved version of the centerline model, which includes the behavior of the joint by permitting relative rotation between the vertical and horizontal elements. However, we also have the Crow-Winkler model, which completely models the web panel dimension, giving a full sense of the node dimension and also the web panel behavior. Our study was made on 3, 6, and 9-story office building frames with 4 bays. The properties of the frames are shown on the side. We designed the perimeter frames, which were responsible to resist the lateral forces. And these perimeter frames were designed to be moment resisting, while the rest was just meant for gravity. In the last bay, which is the perimeter frame, the last bay is considered to be moment released, so does not contribute to the moment resistance. Only the first 3 bays contribute to the moment resistance. Given the regularity in elevation, 2D models have been used, and seismic masses and the gravity loads were transferred to the perimeter frame, while seismic masses were lumped at the joints. A material grade of S355 was used for all elements. Like I said, the last bay was modeled as pin-ended. The beams in the last bay were modeled as pin-ended. A modal response spectrum analysis was carried out in OpenSeas, and the design was carried out with an in-house developed tool written in Python. The structural analysis using response spectrum analysis considers the following. So response spectra type 1 has been used with swell type B and the peak ground acceleration of 0.35 g. Sway imperfections were modeled with a set of lateral forces, and the SRSS method was used to combine the modal maximum. The member designing checks were made as follows. Particularly for moment resisting frames, the columns being the non-dissipative elements, they have been designed to have sufficient overstrength. As such, the design forces have been magnified by the system overstrength omega, which was taken as the inverse of the minimum utilization ratio of the beams. The local hierarchy criteria for beams and columns have also been checked, and the final design shows that the design is mainly governed by the frame stability requirement. Therefore, although the actual resistance of the beams does not require higher cross-sections, the frame stability requirement resulted in bigger profiles. And the damage limitation requirement was also checked to be satisfied with having under 1% interstory drift values. The designed frames have the following sections for the 3, 6, and 9-story frames. After the design, performance assessment was done using pushover analysis with two loading forms, which is one uniform pattern and the other of a modal pattern, where the lateral forces were applied on the frame. Leaning columns were used to capture the P delta effect, and some parameters were controlled throughout the process. For the incremental dynamic analysis, 10 accelegrams or ground motion records were considered and then scaled so that their average would closely match that of the response spectra given in the code. Afterwards, these values were scaled to 3 intensity measures to signify the 3 different limit states: damage limitation, severe damage, and near collapse limit states. And these forces were applied at the joints at the base nodes as a uniform excitation. In the modeling strategies, forced beam column elements were used with fiber sections with 5 integration points per member, so that the design could be carried out at various points throughout the length of the member. And these fiber sections have at least 2 elements across the thickness and greater than 150 fibers overall. The constitutive material models used for the steel in these models were the Meneghetto Pin 2 model, which is S Steel 02 modeled in OpenSys, and Steel 04. In addition to these, zero-length elements, strings, have been used to model moment releases, and also the links to represent the connection, and also the web panel. A step value of 5 mm has been used in the pushover analysis, and a 0.005 second step value that matches the input signal have been used for the incremental dynamic analysis. Regarding the modeling of the connection and the web panel, the properties shown below have been used, and the Equal Joints project further classifies the stiffened joints into 3, with depending on the behaviors of the web panel and the connection topology. So these are joints with strong panel zone and equal strength connections, as you can see here, joints with strong web panel and full strength connections, and joints with balanced web panel and equal strength connection. The modeling strategies used were, for the simplified models, a simple centerline model had been used, and for the models with strong web panels, a refined model that considers the joint dimension has been used. In this model, we used sufficiently rigid elements to represent the web panel dimensions, and for the connections we used links or springs to model the bilinear moment rotation behavior of the connections. In the last model, which is refined, we used the Crow-Winkler-Gupta model, where we were trying to model balanced web panel joints. And in this case, a set of rigid elements were used to model the panel zone peripheries, and 3 hinges have been placed, and in one corner 2 bilinear springs have been combined in parallel to result in the well-known trilinear behavior of the web panels. The results of the analysis show more or less similar performance while under the damage limitation and severe damage limit states, but their differences become evident in the near collapse limit state, as you can see from the figure here. And these differences continue magnifying as the number of stories increase. Nonetheless, the 1% interstory drift limit has been fulfilled in all models throughout the analysis. In summary, I can say the IDA results showed that the frames designed with the equal joints, pre-qualified joints, satisfy the interstory drift limits, whilst the frames with balanced web panel and equal strength connections had shown around 12% increase in interstory drifts. Apart from this, and also on a continued assessment made on other frames after the submission of this paper, we have also noticed that this modeling technique would enable the capture of potentially different story mechanisms in frames. The Pushover analysis results also prove the same results that were obtained from the IDA. Here you can see that the results obtained for the balanced web panel models are relatively of lower resistance, or saying giving higher sway displacements for the same magnitude of base shear compared to the other two models. And it can also be said that the simplified modeling technique was okay for the strong web panel type of joint. The seismic design was repeated, and it shows here again with the strong web panel there was a slight increase in the fundamental period as the frame gains stiffness, and the design base shear increased a bit, while the reverse was true for those with balanced web panels. Nonetheless, the minor increases in the design forces could not surmount the level of over-design that was there due to the stability requirements, and therefore the designs remained unchanged. In conclusion, it can be said that the refined models could be useful in modeling the web panels, and particularly for balanced web panels. However, their designs results, or the overall design results, were not changed, so they had negligible effect. The incremental dynamic analysis showed that the frames designed adequately satisfy code requirements. Compared to the other two, the balanced web panel had larger, around 12% higher increased interstory drift values. In general, it could be said that the simplified modeling technique is okay or sufficient for models with strong web panel, while the refined model is recommended for use in structures with balanced web panel joints. With this, I conclude my presentation, and thank you for your attention.